next speaker is going to be Arthur Parzygnat, and he's going to talk about conditional distributions for quantum systems. I think we can start.
All right, thank you. Thanks for the invitation. And so you've already read the title, and also thank everybody for being here. And so this talk is about conditional distributions for quantum systems, and I'm going to present something that's maybe a little bit foreign. So please feel free to ask questions at any point in time. I don't know if I'll be able to see the chat as I'm giving the talk, so I'll try to take pauses if I can, and people can ask during those times, or whenever, if there's something that's needs to be clarified, definitely feel free to ask. So a lot of this is part of ongoing development in categorical probability theory, where a lot of the axioms of probability theory are sort of going under revision, and in the sense that we're trying to understand probability theory from a completely categorical perspective, where we're not using necessarily the ideas of like measures, measure theory, and the usual notions of probability theory. We're trying to use something, a more abstract language for it. And because of this abstract language, it will hopefully allow us to understand these similar concepts in completely different places. And the place that I'll be focusing these ideas in is in quantum systems. So I'll first refresh by reviewing what Bayes' rule is in a very simple example. And I will then talk about how conditional probabilities can be viewed as morphisms in some category. And not just that, but then how to use that idea and then transfer that over to a quantum setting. And in particular, conditional distributions will be examples of such a thing. And then I'll also talk about more specific examples of quantum conditionals, going from EPR to a slightly more complicated example, which will illustrate some of the features of these conditional distributions. And then I'll talk about a theorem about when these conditionals satisfy a notion of positivity, which is closely related, but a weaker form of what properties quantum channels usually satisfy. And I'll also talk about a brief comparison between these ideas and other ideas proposed for how we can do Bayesian inference or inference in general in a setting similar to this. So let's first start with a very simple example of Bayes' rule. And let's just say Alice is at work and she's tabulated, she's collected the data for the past year. Don't ask me why you would do this, but let's just say Alice has done this, where she records different weather patterns and whether Bob brings an umbrella to work or not. And for example, in this table, I've written the 0.2 for cloudy and Bob bringing an umbrella to work, which signifies that 20% of the days of the year, Bob is bringing an umbrella to work. Those two events happen simultaneously with 20% probability. And you can look at, this data includes, for instance, what are the probabilities of it being sunny, cloudy, or rainy, and that's called one of the marginals of this joint distribution. And for instance, in this case, since 10% of the days are cloudy and Bob brings an umbrella, this ends up telling us that 30% of the days are cloudy, and then there are similar distributions for the other days. And there's another marginal that tells us whether or not Bob brings an umbrella. So how frequently does Bob do that? And in this case, for example, Bob brings an umbrella to work 70% of the time, so quite frequently. Maybe if you live in the UK, this is maybe common, I'm not sure. And with these data, you can also ask and answer a lot of interesting questions. For example, you can ask, what is the probability that Bob brings an umbrella if Alice happens to know it's cloudy, but let's say Bob hasn't come into work yet? And you can also ask a converse question, sort of, which is, what is the probability that it's cloudy if you happen to see Bob bring an umbrella to work, but maybe you showed up to work really early and you don't know exactly what the weather is like. So maybe you see Bob bringing an umbrella. Can you make a deduction, maybe some probabilistic deduction about what the associated probabilities are for that weather? And you can do this by using what's called Bayes' rule. And it involves constructing what are called conditional distributions. And those conditional distributions are obtained by formulas that take the joint distribution and the marginal and do some division process. And so from this perspective, Bayes' rule is viewed as an equation that relates probabilities of certain events and for certain events happening. And rather than viewing, well, we can do a couple of things. First of all, if you might notice that there's a slight abuse of notation that the letter P is used for all of these different mathematical objects. They're closely related, but they're nevertheless different mathematical objects. Like the one in the middle is a joint distribution. There are two conditional distributions, and then there's the marginal probabilities. It's useful to introduce separate notation for all of these different things. And when one does this, it's also natural with some insight that was, I think, due to Cho Jacobs, Brendan Fong, and others, that you can view Bayes' theorem as an equation in a categorical setting in terms of a commutative diagram, where each of these different mathematical objects are morphisms in some category. You can view them as a process. And if you're familiar with string diagrams as well, there were string diagrams actually in some of the earlier talks, where you can also view a commutativity of a diagram as an equality of string diagrams too. And the upshot of viewing Bayes' rule as a commutative diagram is that you can then instantiate Bayes' rule in any category which has the sufficient structure for which we needed to make sense of this diagram. And one such setting is exactly that of quantum systems. So we can rethink Bayes' rule as an existence theorem rather than as an equation. And this existence theorem tells us that if you give me input data in the form of a joint distribution, then I can give you output data in the form of conditional probabilities, which I'm just labeling as F and G, such that a particular equation holds. So it emphasizes this input and output data, and then the equation is just a condition about those distributions. And to find a quantum analog of this, what we'll do is we'll view these conditional probabilities as morphisms, as I've already alluded to earlier. And again, the idea of this notation is that, for instance, if Y was corresponding to the weather patterns, or no, I think it was X that was corresponding to the weather patterns and Y was corresponding to whether Bob brings an umbrella or not, it would be the probability P of Y given X would represent something like the probability of Y equals Bob bringing an umbrella to work, given that X equals this weather pattern. You can view that as a morphism, as a stochastic map that associates to each event X, such as what the weather pattern is, with a corresponding probability distribution on whether or not, on the set Y, whether or not Bob brings an umbrella to work. And so Bayes' theorem can be viewed as the statement about the existence of a morphism satisfying some condition, which is the commutativity of that diagram I had written earlier. And you don't need to know if the diagrammatic formulation is completely foreign to you. You don't need to really understand the technical details of that diagram. Just knowing that it's really a way of saying, given some input data in the form of a distribution or some kind of a morphism, there's output data in some form of a morphism that satisfies some condition that can be applicable in a broader context. And in particular, although an equation such as Bayes' rule might be meaningless in the quantum setting, because we have to understand what are the corresponding quantum objects for each of these mathematical objects that appear, it'll be easier to make sense of commutative diagrams. And what typically replaces states in the quantum setting are things like joint distributions, are things like density matrices and their corresponding marginal density matrices, like if you trace out degrees of freedom. What are perhaps less clear are what would replace these conditional distributions, these probabilities of Y given X's. And there are many proposals for what should replace those. And in this setting, I propose that one could replace them with a morphism or a positive map. And then the other question you have to ask is what replaces this multiplication operation or division, if you were looking at it from that perspective. And that will also have a corresponding notion from this categorical perspective as well. So some of these analogies that are available to us are as follows. So you can start with a finite set X. You can think of that as like representing your phase space or something like that in a classical system. And there's a corresponding algebra of observables on that system. So that forms a C-star algebra, for example. And if C-star algebra is unfamiliar terminology for you, you can just think of it as the algebra of functions on that set, or the algebra of observables. And for each conditional probability, this thing that associates to each element in the domain a probability distribution on the codomain, that'll correspond to a positive unital map. I'm not going to describe you what the formula is for the associated positive unital map, but all you really need to understand is that that's what the correspondence gives you. I'll describe a little bit more about what that correspondence says in a moment. And if you have, for instance, a probabilistic distribution, let's say you don't know your exact state that you're in your phase space, but you have a distribution, then that corresponds to a functional on your algebra, which we think of as computing the expectation value of all of your observables. So very concretely, if we have a matrix algebra as our algebra, and a state on that would therefore correspond to a density matrix, and we're computing with this trace map and the density matrix itself, we're just computing the expectation value of arbitrary observables on our algebra with respect to that state, with respect to that density matrix. There's also a copy map, which just takes an arbitrary element x, and it gives me a distribution on x cross x, which is localized exactly at the element x comma x. So we think of that as a copy map in the classical setting. And although there is no quantum operation in the quantum setting that acts as a multiplication, that acts as a copy map because of the no cloning or no broadcasting theorems, there is nevertheless a linear multiplication map. And notice that these arrows go in the opposite direction. This is just a technicality depending on which viewpoint you're taking, whether you're in the Heisenberg or Schrodinger picture. Since we're talking about the associated algebra of observables rather than the associated states on those systems, I'm just describing this in the Heisenberg picture. But you can see if I had written this from A to A tensor A, one could imagine thinking of this as a copy map. There are also other maps that you can construct in the classical setting that have very natural analogous equivalents in the quantum setting, such as taking a projection, which would correspond to an inclusion in the Heisenberg picture, or tracing out a system, a quantum subsystem, in the Schrodinger picture. And there's a very precise justification for all of these analogies that's given by something called stochastic Gelfand duality, which essentially just says that if you give me a state, I can look at the associated algebra functions. So I've briefly alluded to this. And if you give me a stochastic map, then I can construct for you a positive unital map in the opposite direction on the algebra of observables. And I can go back and forth between these two. And what this says precisely is that there's an equivalence of categories between finite sets and stochastic maps and commutative C-star algebras and positive unital maps between them. And because commutative algebras live inside of the bit larger category of all non-commutative ones, we can take the ideas that we've presented earlier and just transfer those ideas to that larger setting. And that's exactly what we do with the Bayes diagram equation that I had drawn earlier by just replacing all of those sets and stochastic maps with algebras and positive unital maps. So we can make a definition, and this definition is exactly motivated by the one in the classical setting and this categorical perspective combined. So it says that if you give me a joint state on your system, then I can define a conditional distribution of that joint state given one of the algebras, and that's just to be concrete. I'm just going to make a choice here, and it corresponds to a linear map. Think of this as your conditional. Think of this as a conditional probability, but for now we're just going to assume it's linear, so it's not necessarily something that takes states to states, we're just going to assume the bare minimum structure for now for us to describe linearity. And then we'll analyze positivity shortly. And it satisfies a certain condition. And I've drawn that condition either in the diagrammatic formulation or the string diagrammatic formulation. And it's just an equation that gives us one part of that diagram that I had shown earlier. And like I said, there's another conditional where you condition on the other algebra that gives you a similar equation as well. And don't memorize this equation, just know that an equation can be written down for it, and it's all coming from what the morphisms are in this category. So it's just really you plug in what you plug in arbitrary elements and you see what the diagram tells you, and this equation is exactly that. So any questions so far? All right. Feel free to ask still. I know sometimes it takes a moment to ask a question if one comes up. I've been in that same position before as well. All right. So that was a lot of abstract stuff. And let's just look at some concrete examples. So let's take EPR, for instance. In EPR, each of the algebras are 2x2 matrices, and we have a very specific joint density matrix given on the right. And this is describing that Alice and Bob share a state that's in a superposition of spin up and spin down in a particular way. And if we look at each of the reduced density matrices, then they're the totally mixed state for both Alice and Bob. We could ask what the corresponding conditional is in that setting, and it's given by this map here, f of b. And f of b takes the transpose and conjugates by some matrix. And you can check that that equation I had written earlier is satisfied. So it satisfies this mathematical diagram. But you can ask, what are the consequences and what does it mean? Well, if Alice has particular evidence, so she has evidence in the form of a state, which again corresponds to some density matrix, and she can have this evidence or belief either through a measurement, for example, or maybe she just has this information from some source. Then she can use these two pieces of information. She can use the map F, and she could use her belief state chi, and she can compose the two. And if you notice, if you just follow the arrows, this gives us a map from B to C. So this is describing a state for Bob. And it's a state because F is actually a positive map. So for example, if Alice measures spin up, then Bob will measure spin down by just composing these two maps. And similarly, this spin could be in any direction, and Bob will measure the spin in the opposite direction. The interesting thing to note about that example is that F is actually not positive unital, is not a completely positive map. It's only positive unital. And this you could think of this as being a little bit problematic, because typically one thinks of a quantum operation as being completely positive, but positivity is the bare minimum you need to guarantee that states go to states. Complete positivity has alternative information that has to do with what happens when you take larger and larger systems with tensor products. So let's look at another example. This one's a little bit more complicated, but I've just written it out explicitly in case you're curious, but we'll just go through what the idea is for certain special cases. So one can consider such a state with some weighting given by some probability distribution for a state that's shared between Alice and Bob. And you can construct what the associated conditional is. You don't need to know this formula at all. It's just here for reference. But it turns out that this map is not positive. And I've also expressed it in the Schrodinger picture so that it's a little bit easier to check the math if you do end up wanting to check the math, and if I made a mistake. So there's you can rewrite the joint state shared by Alice and Bob in two different ways. And I'm just going to rewrite it this way because I'll give two examples of what could happen if Alice makes two different measurements. You can either use the spin up and the spin down in the z direction, or minus and plus, which correspond to spin down and up in the x direction. So if Alice has some belief in her state and she measures spin down in the x, then the map F will give us an output density matrix for Bob. And the interpretation is that this is her inference for what Bob's state should be based on her belief for her state. And if you look at the state originally expressed in this basis for Alice, you see that if Alice, for instance, measured spin down in the x, then the wave function will collapse and give you an inference in the spin up direction for Bob. So it's consistent with that wave collapse interpretation. For another example, if Alice measures spin up in the z direction, then we can apply the same wave collapse argument, and we notice that it's a linear combination of spin up and spin down with the appropriate probabilities p and 1 minus p. And that's what the standard wave collapse argument would tell you the corresponding state is for Bob. But if you also look at the map F, and based on the diagrammatic formulation, you get a density you get a matrix, sorry, but it's not a density matrix, but it's nevertheless, interestingly, a non-orthogonal projection onto the span of that same vector you would have gotten from the wave collapse argument. So it still has some inferential information, but that corresponding matrix, it's not necessarily a density matrix, and this map is not necessarily positive, but it nevertheless contains this information. So it's important to ask when this map is positive. For which states do you get a positive map? And the states for which you get a positive map, we can also analyze what happens for different proposals for what one could hope for applying some kind of an inference rule. And there are many proposals in the literature. The most obvious one that you can think of for pure states that works quite well is a quantum mechanical wave collapse argument, where you just look at your tensor product, you collapse it onto some state, and then you look at the corresponding state for Bob. Another map that often appears in the quantum information theory literature, and it's also becoming particularly relevant, for instance, in the black hole information paradox, is the Petz recovery map. And there's also the Leifer-Steckens acausal propagation map, which is also another proposal that uses a different approach, and it gives slightly different results. And then there's our proposal. So you can see that the results are not always the same, and one is not necessarily better than the other, but one is perhaps used in a different setting. And so it's important to understand when these maps are positive, and I'll mention another result why it's important on the next slide. And if you give me a joint density matrix, you can ask when a conditional is positive. And if you happen to have a positive conditional, so this is one that can be interpreted as saying, you know, if Alice has some belief for a state, she has an update that's guaranteed to be a state for Bob. And that statement is equivalent to some commutativity condition, which is something that you can check more directly, more computationally. So you would take, for instance, the standard matrix units, plug them in, compute this commutator, and if that commutator always vanishes, then you know that a positive unital conditional exists. It doesn't give you a formula for it, but it tells you that one exists. But that condition is also equivalent to some other interesting condition that has to do with something called Tomita-Takesaki modular theory, which says that if you take this map F that I've written down here as an expression, and if you then apply what's called the modular group flow, which is just taking your density matrix and exponentiating it to some power, and then you conjugate it. It's just some operation that you can do, which also has an important meaning in terms of like evolution, in terms of some Hamiltonian, given by that density matrix. If that's invariant under that conjugation, then a positive unital conditional also exists. So all three of these are equivalent. And in fact, they're equivalent to an even weaker condition, which says that a star preserving or a self-adjoint conditional exists. And there are many upshots of this theorem. And first of all, it gives a simple criteria for checking whether positive conditionals exist. And also interestingly is that on the subset of states for which this map is positive, it happens to agree with one of the alternative proposals for Bayesian inference. And it also makes a connection, as I said, to Tomita-Takesaki modular theory, which is becoming a highly relevant topic in these days in the quantum information theory literature. in other areas as well, like quantum field theory. And on the other hand, we've also had this example where we see that the two predictions given by these different proposals can be different. And this exactly happens on outside of this subspace for which this map is positive. And this is where the two proposals sort of differ. And it's interesting to ask, what general, what differences can actually be seen from these two proposals, and when is one more, how could I say, preferable in a certain scenario than another. And so there are many open questions with these ideas that come from applying categorical probability theory to the quantum setting. Some technical questions you can ask, which are very relevant, but what happens if your reduced density matrices are not invertible? Although the formulas I have written down seem to assume that, but you can ask what happens if that is no longer assumed. You can also ask, what is the general interpretation when it's not positive? I gave an example where you get this projection, but it's not orthogonal, but nevertheless, it has some information that you can use to provide a form of inference. You can also ask what happens for arbitrary finite dimensional C-star algebras, which is partly important because you want to be able to also talk about not just quantum channels between two different spaces, two different quantum systems, but maybe you also want to talk about including measurements or constructing ensembles, POVMs, and that sort of stuff. You can also ask, EPR was a situation where we had a positive conditional. It wasn't completely positive. You can also ask, what is the collection of all joint states that admit positive conditionals from this setting, from this kind of a definition? And a lot of these questions are open because a lot of this stuff is relatively new about using these categorical probabilities to provide a potentially alternative approach towards inference in quantum systems. So with that, I thank you for your attention. For more information, feel free to ask me anything, or you can also check out the archive paper for more information. Thank you.